Hello my dear students, today we'll speak about the electronic configuration of the first transition series elements. So the first transition series elements starts with scandium 21, titanium 22, vanadium 23, chromium 24, manganese 25, iron 26, cobalt 27, nickel 28, and copper 29, zinc 30. So this is very important to memorize. These elements with their electronic configuration and the number of electrons or the atomic number or the number of protons is very important for us to memorize it. Now we will notice something. This thing is 21 2 is the electronic configuration of 4s, and 1 is the electronic configuration of 3d. Titanium here 22, the first digit is the number of electrons in 4s, and the second digit here is the electronic configuration of 3d, so it is 4s2 3d2 after argon. So vanadium 23, 4s2, this digit 2, this is the number of electrons in the 4s, and in 23 the second digit is the number of electrons in 3d. Here chromium, the same rule, but it is abnormal. So chromium 24, it is supposed to be that 4s argon, 4s2 and 3d4. There is no 3d4 or 3d9 in the main transition element electronic configuration. So this is argon and 4s1 3d5. So 3d takes one electron from the 4s2 electrons and forms 3d5. As 3d5 it is half completely filled, so it is more stable, and 4s is half filled, so it is more stable. So there is no electronic configuration in the elementary state of n-1d or 3d4 or 3d9. It is not exist at all. So in this case 4s1 3d5. Manganese 25, so the first digit here 2 refers to the number of electrons here 4s2, and the second digit 5 refers to the 3d5 electrons. In the same rule, 26 iron, so 4s2 3d6. Cobalt 27, so argon 4s2 and 3d7. Nickel, it is 28, so 4s2, argon 4s2 and 3d8. Copper, in the same rule like chromium, but it is here 3d, it is supposed to be 9. Here it is more stable when the 3d sublevel is completely filled with electrons. So it is assumed that 4s2 and 3d9, there is no 3d9 and there is no 3d4. So here 29 argon 4s1 3d10, because it is more stable than 4s2 3d9. And zinc here 30, it is argon 4s2 and 3d10. Okay, here we follow the Hund's rule. Hund's rule refers to the filling of electrons in the same sublevel in orbitals singularly. Single electron in each orbital. This is 1 electron scandium, 2 electrons in 2 orbitals in titanium, 3 electrons in 3 orbitals individually in vanadium, and so on. Here chromium is supposed to be 4, but it is more stable when it contains 5 electrons, half filled. 3d contains 5 orbitals and contains 5 electrons. So for chromium, in case of chromium, it is 4s1 and 3d5. Okay, afterward manganese 25, 4s2 and 3d5. Pairing takes place from iron 4s2 and 3d6. The 6 electrons here in the 3d, 1 electron, 2, 3, 4, 5, and the 6th electron occupy this orbital. Here in cobalt the same, but there is 2 electrons, as 3d contains 7 electrons. So 5 electrons occupy singularly the 5 orbitals of the 3d, and then the etc electrons occupy the first and second. Here nickel occupies 3 occupies five orbitals with five electrons, and the rest of the 8 electrons occupy the first, second, and third electron. Here in copper, 4s1 and 3d10 completely filled. All electrons exist in a spin paired state. Zinc, 4s2 and 3d10, so also it is spin paired state. So there is an abnormal electronic configuration. This abnormal electronic configuration appears in chromium and appears in copper 29. In chromium it is half filled, so it is more stable. So 4s here in the elementary state contain only one electron, not two electrons. Here copper 29, it is supposed that 4s2 and 3d9, but here copper, when it is completely filled and contains a 3d sublevel, completely filled and contains 10 electrons, it is more stable. So its electron configuration actually is 4s1 3d10. Okay, so the factor that when the electron configuration of the 3d is half filled is more stable, we can understand through this idea what happened when the iron is oxidized. Is it really oxidized from positive 2 to positive 3, from ferrous to ferric? Yes, it is 26 electrons. So argon 4s2 and 3d6. So when it loses 2 electrons, it loses first from 4s2, then it loses from the 3d electrons. So iron positive 2, it is argon electron configuration 3d6. It is more stable when it loses another electron here and becomes 3d5. It is more stable as it is half filled. Okay, so ferrous can easily converts or transferred into ferric. Iron positive 2 easily oxidized into iron positive 3. Okay, as iron positive 3 is half filled and more stable. In case of manganese 25, and its electron configuration argon 4s2 and 3d5. So when it loses the first 2 electrons, it loses the 2 electrons of 4s. So the electron configuration of manganese positive 2 is argon 3d5. When it is oxidized to manganese positive 3, the 3d sublevel converts or transferred from 5 electrons, which is half filled more stable, into less stable ion, which is 4 electrons in the 3d, which is less stable. So it is difficult for manganese, which is more stable, has an electron configuration with half filling of 5 electrons, okay, and to transfer to a less stable ion, which is positive 3, when the 3d sublevel is less than half filled, so it is less stable. So iron can be oxidized from iron positive 2 to iron positive 3. In case here of manganese is very difficult to be oxidized from positive 2 to positive 3, as positive 2 is more stable than positive 3, as it contains 5 electrons, means half filled and more stable. So in general speaking, what happened here, the electron configuration of when it is half filled or completely filled is more stable. Half filled here, like chromium 4s1 3d5, manganese argon 25, argon 4s2 3d5, or positive 2 3d5 only, and ferric or iron positive 3, which is composed 26 electrons, losing 3 electrons, 2 from 4s and 1 from 3d6, so it converts into 3d5. Here, when it is completely filled, like copper 4s1 3d10, or copper positive 1 4s0 and 3d10, or zinc 3d10, or zinc positive 2 4s0 and 3d10. So 3d, when it is half filled or completely filled, it is more stable. However, this is not the only factor of the stability of the ion or the atom. So here is a very to some extent important notice to know. Although copper positive 1 3D is completely filled 3D10, it is less stable than copper positive 2, which has 3D9, as the hydration energy, which is the energy released when the copper positive 2 combines with water molecule, is higher than the energy released when copper positive 1 combines with water. Okay, let's take this information into consideration. Okay, so there is some questions we have to answer here in terms of the electron configuration of M positive 3. M positive 3, its electron configuration is argon 3d3. So what is the atomic number of this transition element? By generally speaking, M positive 3, it loses 3 electrons to be in the elemental, to convert from the elemental state to the positive ion. And its electron configuration contain argon 18 and 3d3, 3 electrons here in the 3d, plus 3 electron lost when it is converted from the elemental state to this ion. So argon 18 plus 3 electrons, the 3d, add to them 3 electrons to be in the elemental state, which has been asked about this transition element. 18 plus 3, 21, plus 3 electrons to form the elemental state with no charge 0, it equals 24. Okay, 24 refers to chromium. When chromium, its electron configuration is 4s1 and 3d5. When it loses 3 electrons, so it leaves or loses 1 electron from the 4s and 2 electrons from the 3d, which is half filled. So 3d here has 3 electrons only. So the correct answer is 24. Now there is very important notes about the oxidation state. Now we know all that the 4s and 3d sublevels are close in energy. So when the atom is provided with some energy, it loses the 4s electrons first because it is farther from the nucleus. Then it loses 3d, but they are close in energy. So when the energy is supplied to the atom, it may lose 2 electrons from 4s, and afterward it will lose another electron easily from the 3d in successive way. So because of that, it can be oxidized in several oxidation states. So let's speak here about the oxidation state. Oxidation states of all these elements, transition elements: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. The common oxidation state is positive 2, and this refers to the losing of the 2 electrons of the 4s in general. The only exception for that is scandium, positive 3. Its electron configuration argon 4s2 and 3d1. It loses all the 3 electrons, 2 electrons from the 4s and 1 electron from 3d. So its only oxidation state is positive 2, and this is a very, very important notice. It is repeated in the exams. The only main transition element, typical transition elements, which has only one oxidation state, is scandium. It is not zinc. Zinc is not considered as a typical main transition element, but here scandium considered as a main transition element, and only its oxidation state, the only oxidation state for it is positive 3. Now the oxidation state increases as we go from left to right until manganese. Then it turns into positive 2 and positive 3 in copper, in cobalt and iron, and nickel here positive 2, and there is some little or some random or some rare some rare oxidation states, positive 3 and positive 4 for nickel here, but the main or the common oxidation state for nickel is positive 2. Copper positive 1 and positive 2. Zinc is positive 2 only. Okay, so here 4s1 4s2 3d1, it loses the 3 electron. Here 4s1 3d2, it may lose 4 electrons from the 4s, or so it may lose 2 electrons from the 4s, and it may lose 2 electrons from the 4s and 1 electron from the 3d, or it may lose 2 electrons also from the 3d. Okay, vanadium here 4s1 3d3, it may lose 2 electrons from the 4s first and acquire the oxidation state of positive 2. It may lose 2 electrons from the 4s and 1 electron from the 3d, or 2 electrons from the 3d, or 3 electrons, all the 3 electrons which exist in the 3d, it may lose the 3 electrons. So it acquired the oxidation state of positive 2. Chromium, its main oxidation state is positive 2, positive 10, positive 6. Here the high oxidation state in this group is manganese. It is in group 7b. Group 7b here composed of positive 2 main oxidation state and positive 4 and positive 7. Here we notice that there is a rare oxidation state of positive 3 and positive 6 according to chromium, according to manganese here, okay, but there is no oxidation state of positive 5. We have to put it into our consideration. So the main oxidation state for manganese is positive 2, positive 2, 4, positive 7. Iron is oxidized into ferrous and ferric, or positive 2 and positive 3. Cobalt is like iron in the oxidation state. It is positive 2 and positive 3. Nickel positive 2 main oxidation state. Copper positive 1 and positive 2. Zinc positive 2 only. Here we have to notice that this oxidation state of iron, if it exists, we call it ferrous, and this oxidation state positive 3 we call it ferric. Here in copper positive 1 we call it cuprous, and positive 2 we called it cupric. Okay, we may call the compound copper 1 or copper 2 sulfate, or copper 1 or copper 2 chloride. We may speak that iron 2 sulfate, iron 2 nitrate, iron 3 hydroxide. Okay, this is the oxidation state and the number of charges which exist on the atom or ion. So here we have to notice that positive 2 is a common oxidation state for all the elements of the first transition series except for scandium. Okay, oxidation states increases from left to right to manganese, then decreases in zinc positive 2. The only typical element, the only typical main transition element which only has one oxidation state is positive 3, scandium. When you ask it in the exam, a main transition element in the first transition series contains only one oxidation state. It is 100% scandium. Okay, so there is a lot of oxidation state or several oxidation state because the successive losing of 4s and electrons and 3d electrons which are near in energy. Okay, 4s sublevel is near in energy to the 3d sublevel. Okay, here the oxidation state does not exceed the number of the group. This is except the coinage metal group. This is coinage metal group. Here we see that 3b and the main oxidation state does not exceed 3. 4b in titanium and the highest oxidation state does not exceed positive 4, which is the number of the group. Here group 5b and the high oxidation state for vanadium does not exceed the number of the group. And here the same chromium group 6b, its high oxidation state is positive 6. 7b for manganese, high oxidation state is positive 7. It does not exceed that. Here the only exception is copper and silver and gold. In some cases exceeds the number of the groups, which is 1b. Its common oxidation state for copper is positive 2. Okay, so let's have some questions. Manganese has the highest oxidation state in the salt of Okay, manganese here, we have to calculate the oxidation state of manganese. We know that oxygen, each oxide ion have a charge of -2. -2 multiplied by 3 atoms here, or ions of oxygen, so it is -6. So manganese here is +6. Okay, manganese here, oxygen -2 and manganese +7. This is the oxidation state of manganese, and this is too the oxidation state of oxygen. So this is the highest oxidation state. But here you asked about the salt. It is not the salt, it is an oxide. Okay, so potassium permanganate here, this is +1, potassium +1. 4 oxygen atoms, each one of them has -2 multiplied by 4, so it is -8, +1. So the whole charge, the net charge after the summation of potassium charge and oxygen charge, -8 and +1, -7, and the whole molecule is neutral, -7. So manganese in this case has an oxidation state of +7, and it is a salt, and it is the highest oxidation state. Here the opposite graph figure represents the ionization potential of main transition element. What is the use of this element? So here we have to look at the energy here. The ionization potential is the energy required to release the first electron, the energy required to release the second electron, the energy required to release the third electron, the fourth electron, the fifth electron. Here, when we want to release or get rid of the sixth electron, the energy go very high, so it is a complete energy level. So the outer electrons here is 5 electrons. So 5 electrons, it is, if you think with me, it is 4s2 3d3, and it is the electron configuration of vanadium, which is used in car springs. Okay, so the use here of this element, it is vanadium, and it is used in car springs. As you remember with me, that vanadium, its symbol is V, and the car springs like V in shape. Okay, here we'll speak about the oxidation states of the transition elements. It increase gradually, so it will happen with no problem. Vanadium may have 2 oxidation states, +2, +3, +4, +5. But if you look at the representative elements like magnesium, sodium, and aluminum, there is a very difficulty to acquire the second oxidation state, or +2 sodium, +3 magnesium, and aluminum +4, as when we want to acquire sodium +2, we will break a completely filled electron shell. It requires very, very high energy, so it cannot happen in normal condition. The same is the third ionization potential of magnesium and the fourth ionization potential of aluminum. So here scandium element does not form compounds with +4, as it is the electron configuration of argon 4s2 and 3d1. Okay, there are 3 electrons, 2 electrons here in the 4s and 1 electron in the 3d, so we can remove them and acquire +3 scandium. +4, we have to break a completely filled shell, which is 3p, which requires very, very high energy. It cannot happen in normal condition. So what is the definition of the transition element? The definition of the transition element, it is the element which has the electronic configuration of D or F occupied with the electron, but not completely filled with the electron, either in the elementary state or in one of its oxidation state. So in general speaking, when we see that an element has in the last sub-level, electrons in the d sublevel or f sublevel, and they are not completely filled in their atomic state or in one of its oxidation state. In this case, it is a transition element. Try to memorize this. Occupy but not completely filled. They are the elements in which electrons occupy d or f sublevel but not completely filled with electrons. This is the transition element. And according to that, do we consider that the copper, silver, and gold a main transition element? Yes. The main transition element means it is occupied but not completely filled, like copper in positive 2 and silver in positive 2 and gold in positive 3. They are not completely filled in one of their oxidation states, so they are considered as a main transition element. Main transition element means in one of its oxidation states there is electron in the d sublevel, but they are not completely filled, occupying but not completely filled. But here in group 2b, they are not considered as a typical main transition element, as they has only positive 2 oxidation state in case of zinc, and in case of cadmium 48, and in case of mercury 80. So in both the atomic state of zinc 30, cadmium 48, and mercury 80, it is in the elementary state contain completely filled the electrons in the d sublevel, and in its only oxidation state, which positive 2, its d sublevel is also completely filled with electrons. So in this case, zinc 30, cadmium 48, and mercury is not considered as a typical main transition element. So let's have some example about this. Okay, a chemist claimed that he had discovered a new X element, an element X could be included in the periodic table below scandium element, depending on 4 observations, which are 1, 2, 3, 4. So these observations suit this element except. Okay, except means we'll choose the wrong answer. Okay, the number of occupied energy levels in this atom is higher than scandium. It is in the same group but down in the periodic table, so it must contain energy levels higher than scandium. So this is correct, but we want here the exception, so we will not choose this. It has more than one oxidation state. We know that scandium has only one oxidation state, so this saying is wrong. It has only one oxidation state, which is positive 3, but we want the exception, so we'll take this. This is the first one. We'll take this one. Okay, 2. It is wrong, but it is correct because we want the wrong. Okay, the third option is its outermost electron configuration follows the system ns2 n-1 d1. Scandium, if you remember with me, it is 21 argon 18 4s2 and 3d1. Yes, 4s2 and 3d1. Yes, okay, ns2 and n-1 d1. Yes, it is okay, it is correct. Okay, so correct, so we cannot take it, as we want the exception. It reacts with oxygen forming XO2. Here the oxidation state of this element, positive 4 as 2 oxygen atoms, each one has a charge of negative 2 multiplied by 2 negative 4, so it is positive 4. The only oxidation state of this group is positive 3, so number 4 is wrong, but here we want the exception, we want the wrong, so this is, we will take with us, it is wrong, and he wants the exception. Okay, so the correct answer is the answer of 2 and 4. This is the answer, so the correct answer here is C. Here, which of the following sets groups of elements includes one of the main transition elements? So, okay, iron 4s2 and 3d6, 26. Cobalt after iron 27, 4s2, 3d7. Nickel 4s2 and 3d8. So 3d or d sublevel is occupied with electron but not completely filled. There are three main transition elements. Copper considered the main transition element. Silver in the same group, the main transition element. There is two elements here of the main transition elements. It is not one, two elements. In the first choice, the three elements from the main transition series. Here is zinc is not considered from the main transition series. Manganese and titanium considered from the main transition series. So this option contains two elements which is considered of the main transition series. It is not one element as it is mentioned here in the question. So thorium is from the inner transition element. Its electron configuration is 5f1, so it is not from the main transition element. Its atomic number is 90. Lanthanum 57, it is under scandium in the periodic table. It is 6s2 and 5d1. It is considered as a transition element. Okay, this is one transition element. Mercury in the group of zinc 30, cadmium 48, and mercury 80. They are not considered in group 2b. They are not considered as a main transition element. So the correct answer here is D, which contains only one transition element in this group. So this is the correct one. Here another question. Okay, which of the following electronic configuration of a main transition element? We have to know that main transition element means we have the D. Look, the question here, which of the following electron configuration of main transition element? He asked about the elemental state. It is not the oxidation state. So we have to see here D sublevel, and D sublevel occupied but not completely filled, but not completely filled. Okay, here there is no D sublevel, so it is wrong. Here there is no D sublevel, it is wrong. Here there is a D sublevel, but it is completely filled with electrons. It is not considered as main transition element. It is from 2b, like zinc, cadmium, and mercury. So they are not considered as main transition element. Here n positive 1, n plus 1 s2, n d3, it is the group of vanadium, group 5v, and they are considered as main transition elements. So the correct here is B. Let's have another question. All the following about the coinage element are correct except copper positive 1 can easily oxidize to copper positive 2. To copper positive 2, yes, it is the more common oxidation state, so it is easily oxidized. Okay, gold hardly oxidized to gold positive 1. Gold, its common oxidation state is positive 3, so it can easily oxidize and leave 3 electrons. So leaving only 1 electron, it is very easy for gold to be oxidized to gold positive 1. Silver is easy oxidized into silver positive 2. The main oxidation state for silver is positive 1, and it is very hard to oxidize silver into silver positive 2. So this is the wrong answer, and this is the correct answer we will choose. Okay, so silver is easily oxidized into silver positive 2? No, silver is hardly oxidized into silver positive 2. So in this moment, at this moment, we finish our session. Thank you.